Hello all. In this video, I'm going to introduce the ideas of local search. So this is a variation on the state space search that we've been looking at, but it looks at problems in a slightly different way. We use different algorithms that have different properties, and we'll talk about all that in just a moment. All right, so first of all, just to note that we've been talking about in state space search. We have imagined the state space as a set of discrete descriptions of the environment an agent lives in, and our task has been to find a path through the state space to a goal state. So because we're looking for a path to the goal state, that path, the sequence of actions that get you from the start to the goal, is what we're trying to optimize. And that is the solution. So we need to keep track of the path that's being taken because that's part of why we're doing the search in the first place. Local search is different. So with local search, we conceive of the state space a little bit differently. It's still a space of states, and there are actions of one kind or another that allow us to call two states neighbors, but those are usually less directly tied to what our agent might be doing than is the case when we just think of the kind of state space search we have been discussing. So with local search, a state space is the space of possible solutions to a problem. And each solution has some quality to it, some value. And so the higher the value, the more we like that solution. And we have to have what's sometimes called an objective function. It goes by different names. Sometimes it's called an objective function. Sometimes it's called an evaluation function. Sometimes it's called a fitness function. But the idea is the same in all of those contexts. Whatever we call it, it's a function we can pass a state to, and it will determine the quality of that state and return a numeric value. So our task in this case, since each state represents its own potential solution, we want to look through the states as efficiently as we can and find the best possible solution. So it's the state itself that holds the solution. And so we don't really care about the path that we take to find that state. We just want to maximize the state and get the best value, the best objective value for the state that we can. So the path is unimportant. The states we pass through are unimportant, except in as far as we'd like to find the best solution quickly. We don't actually care about what those states are or what the actual path is. All we care about is the best state we find and what its objective function value is. All right, so there are definitely problems that are better approached in this way than by a traditional state space approach. So examples of those include the n-queens problem, which we're going to look at in person. I'm going to talk through the traveling sales problem, which is another classic example. But there are lots of other examples where this is a really useful way to conceive of the task. And one thing I want to point out is that we can actually rethink, and I'm going to split things a little so I can make sure this is all on one page. We can rethink how we conceive of problems we've already been looking at so that they fit the local search approach. So we could think about path finding, route finding, and describe it as a local search problem. The trick is that the states become not locations that we're trying to path plan between. Instead, each state represents a potential solution, a possible path. And so our state space is the space of all possible paths in the space that we have. That is, in fact, an infinite space, potentially. And our objective function evaluates each state based on how close it comes to the goal and perhaps how long it is. So this is a different way of thinking about path planning, but in fact, you can turn many of the problems we've been looking at into local search problems and apply these algorithms as an alternative to the kind of graph search algorithms that we've been doing. we are going to look at a number of different algorithms that can tackle local search problems. Most of them are not guaranteed to find the optimal solution. We kind of let optimality go when we go into the local search realm. We want to do the best we can, but it may be that we for one reason or another, don't happen to find the optimal solution. So the main foundational algorithm for this task is called hill climbing. It has an analog gradient descent. You may hear about gradient descent a lot in the context of machine learning, because that's sort of what many of the machine learning algorithms are doing, is performing a form of gradient descent. We are also going to look at beam search and genetic algorithms. There are other techniques such as simulated annealing and multiple variations on hill climbing itself. So these are the main problems that we want to tackle. What do we need for hill climbing specifically, or perhaps for any of these local search algorithms? We need, much like we did before, we need to be able to represent the state, a state, and we need a way to generate neighbors of a state. So that's very similar to what we've done before. That's just part of it being a state space. We need an objective function. I'm actually going to add something here, because it is in some other sources referred to as an evaluation function, not an objective function. We need a function that we can use to evaluate the quality of a state. It's really important that this function produce a range of values across a range of states. It's not helpful at all to have an objective function that says, yes, 100 points when it sees a solution, and it says 0 points when it sees anything else. We need there to be gradations of quality in order for these algorithms to work correctly. So that takes a little bit of effort on our part to come up with a proper evaluation function for the search that we want to do. We also need a process that allows us to select new neighboring states from the current one in such a way that we eventually lead to some maximal solution. It may not be the absolute optimal, but we want it at least to be a local maxima. And we'll talk a little bit more about that in a bit. How does gradient descent relate to this? Well, I said before, it's an analog. Gradient descent is essentially hill climbing turned upside down. So in hill climbing, we're trying to maximize. It's an optimization method that's maximizing some quality. With gradient descent, we typically think of measuring error or some negative property of the state, and then we want to minimize error or minimize that negative property. And when we do that, it's exactly the same process as hill climbing. It's just that we've flipped our world upside down. So instead of going up the hills, we're trying to go down into the valleys. It might be helpful for us to try to visualize what our state space might look like and how the objective function plays into it. So you'll see these diagrams fairly commonly as a simplified version of what the state space actually looks like. So in this particular picture, which I borrowed from notes from Indiana University Bloomington from their AI course, I just thought it was a nice picture. We have a state space in this case where we've simplified it. We're pretending that it only has 2 dimensions. Basically, it would have 2 features, and they vary on those 2 different dimensions. This is way too simple. Most problems have dozens, if not hundreds or thousands of features, so they are actually like 12-dimensional, 100-dimensional, 1,000-dimensional spaces, but we can't really conceive of that. So we're going to go with 2. So we have a state space with 2 dimensions, and then in the vertical is the values of the objective function. So what this is trying to show you is this kind of a space that's got valleys and hills. It might have saddles, which are particularly problematic for local search. It has some areas where things might be flat. So this is the flat plateau at the top. You could also have flat plateaus in valleys, or you can have a plateau that's a shoulder, so that there is actually a value in passing across that and continuing then to increase higher. So at a particular moment in our search, we're going to have a particular state that we're thinking of, the current state. And you can see the little arrows pointing out. Those are sort of pointing in all different directions to show the neighboring states are the ones that are adjacent in the state space, and they may have varying different values than the one that we're at. And so what we want is to choose to move from our current state to a new state, one of these, in such a way that we increase our quality, we increase the value of our objective function. The other things you can see here is we can see here's a very tall peak, and the value up here is in fact our global maximum. That's what we would really like to find. That's the optimal solution. But there are also other peaks. There's this one right here. There's the one in the back. We call those local maxima because they are peaks. When you get to them, all of the other neighbors that you have are of lower quality than the one that is at the peak, but they are not as high as our global maximum. So we have to watch out for that. We can easily find a local maxima, and it may not be as good a solution as we would otherwise like to see. But as we are working with these search algorithms, we have to think about the ramifications of how we choose what direction to go, and how that interacts with the shape of the space itself to determine whether the search is going to be successful or not. All right, I'm going to pause there. In the next video, we'll actually take a look at hill climbing as an algorithm, and we'll look at some problems that you can apply with hill climbing just to get us started on how this whole local search thing works. I'll see you very soon.